Artificial intelligence is rapidly transforming the manufacturing sector, reshaping how factories operate, how products are built, and how supply chains are managed. For much of the 20th century, manufacturing improvements were driven by mechanical engineering innovations, automation through fixed industrial machinery, and process optimization methods such as lean manufacturing. Today, a new transformation is taking place, often described as the transition towards smart manufacturing or Industry 4.0. At the center of this transformation is the integration of artificial intelligence with sensors, industrial robotics, cloud computing, and large-scale data analytics. Manufacturing environments produce vast quantities of operational data. Machines generate information about temperature, vibration, torque, pressure, and operational speed. Production lines record throughput rates, downtime events, and defect rates. Supply chain systems track raw material availability, transportation schedules, and inventory levels. Historically, much of this data was either unused or analyzed only at a very basic level. Artificial intelligence systems allow manufacturers to analyze these data streams in real time and uncover patterns that improve operational efficiency, product quality, and equipment reliability. One of the most important applications of AI in manufacturing is predictive maintenance. Industrial machines are expensive and often operate continuously for long periods of time. When a critical machine fails unexpectedly, it can shut down an entire production line, causing costly delays and lost productivity. Traditional maintenance strategies generally fall into two categories: reactive maintenance and scheduled maintenance. Reactive maintenance involves repairing machines only after they break down, which often leads to unexpected downtime. Scheduled maintenance involves servicing equipment at fixed intervals, regardless of whether the machine actually needs repair. Predictive maintenance represents a more advanced strategy. Instead of relying on fixed schedules, predictive systems monitor the condition of equipment continuously using sensors that measure variables such as vibration, temperature, acoustic signals, electrical current, and mechanical stress. Machine learning models analyze these data streams and learn patterns associated with normal operating conditions as well as early signs of equipment degradation. When the system detects anomalies that resemble patterns observed before previous failures, it can generate alerts indicating that maintenance should be performed soon. This allows technicians to repair or replace components before the machine actually fails. Predictive maintenance can significantly reduce downtime, extend equipment lifespan, and lower maintenance costs. In large manufacturing facilities with hundreds or thousands of machines, the financial impact of these improvements can be substantial. Another major area where artificial intelligence is transforming manufacturing is quality control. Ensuring consistent product quality is essential in industrial production. Traditionally, quality inspection relied heavily on human inspectors who visually examine products for defects. While human inspection can be effective, it is also subject to fatigue, inconsistency, and limited speed when dealing with high-volume production lines. Computer vision systems powered by deep learning are increasingly being used to automate quality inspection processes. Cameras installed along production lines capture images or video of products as they move through different stages of manufacturing. Convolutional neural networks analyze these images to detect defects such as scratches, cracks, misalignments, missing components, or surface irregularities. These systems can inspect products much faster than human inspectors and with a high level of consistency. In some industries such as semiconductor manufacturing, automotive production, and electronics assembly, even microscopic defects can affect product performance. AI-based inspection systems can detect subtle patterns that may be difficult for humans to identify. In addition to detecting defects, computer vision systems can also provide valuable insights into production processes. By analyzing large datasets of inspection images, AI models can identify recurring patterns that suggest underlying process issues. Engineers can then adjust manufacturing parameters to reduce defect rates and improve overall product quality. Artificial intelligence also plays a critical role in optimizing manufacturing supply chains. Modern manufacturing operations depend on complex networks of suppliers, transportation systems, warehouses, and distribution centers. Disruptions in any part of this network can lead to delays, shortages, or increased costs. Machine learning models analyze historical supply chain data along with real-time information from logistics systems, weather forecasts, economic indicators, and transportation networks. These models can predict potential disruptions and recommend adjustments to procurement strategies, shipping routes, or production schedules. For example, predictive models may estimate the likelihood that a supplier will experience delays due to production constraints or external events. If the risk of disruption is high, the system can recommend alternative suppliers or adjust inventory levels to maintain production continuity. Inventory optimization is another area where AI contributes to supply chain efficiency. Manufacturers must balance the need to keep enough raw materials and components available with the cost of storing excess inventory. Machine learning models forecast future demand and recommend optimal inventory levels across different facilities. These predictive capabilities allow manufacturers to operate more flexibly and respond quickly to changes in market demand. During periods of uncertainty or supply chain volatility, AI-driven forecasting can provide valuable guidance for maintaining stable production operations. Robotics automation represents another major intersection between artificial intelligence and manufacturing. Industrial robots have been used in factories for decades, particularly for repetitive tasks such as welding, painting, assembly, and material handling. Traditional industrial robots typically follow pre-programmed instructions and operate in highly structured environments. The integration of AI techniques is enabling a new generation of more flexible and adaptive robotic systems. Machine learning algorithms allow robots to learn from data and improve their performance over time. Computer vision enables robots to perceive their surroundings, recognize objects, and adjust their actions accordingly. For example, AI-enabled robots can identify and pick up irregularly shaped objects from bins, a task that previously required highly specialized mechanical systems or manual labor. These capabilities are particularly valuable in industries such as logistics and electronics manufacturing, where products may vary in size and orientation. Collaborative robots, often called cobots, represent another important development. Unlike traditional industrial robots that operate in isolated safety cages, cobots are designed to work alongside human workers. AI-based sensing and perception systems allow these robots to detect human presence and adjust their movements to avoid collisions. In collaborative environments, robots can handle physically demanding or repetitive tasks while human workers focus on activities that require judgment, creativity, and problem-solving. This combination of human and machine capabilities can improve productivity while maintaining flexibility in production processes. Artificial intelligence also supports process optimization across entire manufacturing systems. Production lines consist of many interconnected steps, each with its own operational parameters. Small changes in machine settings, production speeds, or material flows can affect overall efficiency and product quality. Machine learning models analyze large datasets generated by manufacturing equipment to identify relationships between operational variables and production outcomes. These insights can be used to optimize machine configurations, reduce energy consumption, minimize waste, and improve throughput. In some advanced manufacturing environments, reinforcement learning algorithms are used to continuously adjust process parameters in real time. These systems experiment with different configurations and learn which settings produce the best results under changing conditions. Energy management is another area where AI contributes to manufacturing efficiency. Industrial facilities consume large amounts of energy for heating, cooling, lighting, and machine operation. AI systems analyze energy usage patterns and recommend strategies for reducing consumption while maintaining production performance. For example, predictive models can identify times when energy demand is likely to increase and adjust machine schedules accordingly. AI can also optimize heating and cooling systems based on environmental conditions and production requirements. Despite the many benefits of AI in manufacturing, implementing these technologies presents several challenges. One challenge is integrating AI systems with existing industrial infrastructure. Many factories operate equipment that was installed years or even decades ago, and connecting these machines to modern data analytics platforms may require significant upgrades. Data quality and availability also play a critical role. Machine learning models require large volumes of accurate and well-structured data. In some cases, manufacturing data may be incomplete, inconsistent, or stored in incompatible systems. Organizations must invest in data collection, storage, and governance systems to support AI applications effectively. Cybersecurity is another important consideration. As factories become increasingly connected through digital networks and cloud platforms, they may become targets for cyber attacks. Protecting industrial control systems and sensitive production data is essential for maintaining operational security. Workforce adaptation represents another key aspect of the transition toward AI-driven manufacturing. As automation technologies become more advanced, the skills required in manufacturing jobs are evolving. Workers increasingly need knowledge of data analysis, robotic systems, and digital technologies alongside traditional mechanical skills. Many organizations are investing in training programs to help employees develop the skills needed to work effectively with AI-powered systems. Rather than eliminating human roles entirely, AI often shifts the nature of work toward more technical and analytical tasks. From an economic perspective, artificial intelligence is contributing to a new wave of industrial productivity. By reducing downtime, improving quality, optimizing supply chains, and automating complex tasks, AI technologies can significantly increase manufacturing efficiency. These improvements may lead to lower production costs, faster product development cycles, and greater global competitiveness for manufacturing companies. Looking ahead, the role of artificial intelligence in manufacturing is expected to continue expanding. Advances in edge computing will allow AI models to run directly on industrial devices, enabling faster decision-making without relying on centralized cloud systems. Improvements in sensor technology will provide even richer streams of operational data. Digital twins represent another emerging concept in smart manufacturing. A digital twin is a virtual representation of a physical system, such as a factory or a machine. AI models analyze data from the physical system and simulate its behavior in the digital environment. Engineers can test different scenarios in the digital twin to identify optimal operating conditions before implementing changes in the real system. The combination of artificial intelligence, robotics, advanced sensors, and interconnected digital systems is gradually transforming traditional factories into intelligent production environments. These smart factories are capable of monitoring their own operations, predicting problems before they occur, and continuously improving performance through data-driven insights. In this evolving industrial landscape, artificial intelligence is not simply another automation tool. It represents a fundamental shift in how manufacturing systems are designed, managed, and optimized. By enabling machines to analyze data, learn from experience, and adapt to changing conditions, AI is helping create a new generation of manufacturing systems that are more efficient, resilient, and responsive to global market demands.
If you find this video exciting, please like, subscribe, and turn on notifications. See you in the next AI for Beginners educational video.